Good evening, everyone. I am Qinyue from Shanghai Jiaotong University. It is a great honor to speak here. Today, I'd like to introduce our paper, Learning to Recommend Trigger Action Rules for End-User Development, a knowledge graph-based approach. Firstly, I will introduce the background of the paper. Secondly, I will detail our approach. Thirdly, I will analyze the evaluation of the work. Finally, I will give a conclusion and introduce our future work. Nowadays, a lot of researches have been done to help professional programmers reuse codes, documents, and so on. However, there are few works focusing on enhancing software reuse for end users. While software reuse and end user development, which is emerging recently, is important too. End user development allows end users without programming experiences to develop their own software artifacts. One popular paradigm in the IoT world is trigger action programming. TAP. It allows non-professional end users to program by themselves in a form of a set of trigger action rules for automating IoT devices and online services meeting their needs. In TAP, a program consists of one or more rules in the form of if trigger then action. Thus, in each rule the user specifies a triggering event and the action that should be carried out. The key elements of a TAP rule are trigger channel, trigger, action channel, and action. Here, trigger, channel, and action channel are specific devices or services. Trigger and action are the functions of channels. For example, a user who wishes to receive a reminder email when a phone call is missed can write a rule like the rule example in the figure. However, the number of the IoT devices or services is growing rapidly, so do the functions they offer. The high-volume tap functions are difficult to learn, remember, use, and especially combine them during the development. Furthermore, while numerous reusable rules are available in the tap communities, such as IFTTT and Zapier, it is difficult to find an appropriate rule for user-specific tasks without any supporting tool. So far, almost all communities only provide the hottest rules and search services by exact rule matching. It is promising to collect these rules and recommend appropriate ones to end users during their development. And our work aims at recommending tap rules when the user is editing a tap program. We collect a dataset from IFTTT and perform a preliminary empirical study. We use a web crawler to collect trigger action rules shared in IFTTT and create a dataset tap data. Tap data contains 72,107 rules created by 39,480 authors. Each rule, as the table shows, specifies the trigger, channel, event, and description, and the action, channel, event, and description. Auxiliary data items are also collected, including the author who has created a rule, the creation time, and a description of the rule. The analysis of top data reveals there exist three challenges when using trigger action rules. Firstly, most users only created few rules. How to recommend rules to cold users with few rules challenges. Recommender systems are mainly categorized into collaborative filtering-based recommender systems and content-based recommender systems. However, collaborative filtering-based methods predict the preferences of rules for a particular user based on the history user-rule interaction information, while content-based methods often analyze the user's history behavior to extract the user preferences and then compare them with the content of rules. This cold start problem challenges to personalized recommendation of tap rules. Secondly, one user often write the same rules for several times with only different parameter values. For example, if a user wants to turn on the lights when he enters rooms, he has to repeatedly write rules with the same trigger and action, and different values of the parameters, trigger attributes to specify each room. Therefore, recommending rules that users use before makes sense. This repeat consumption problem shouldn't be often ignored by tap recommender systems. Thirdly, there are quite a few conflicts amongst multiple rules existed in tap programs, whether written by novice users or experienced users. For example, a user wrote a tap rule to open the windows of home every morning, while forgetting to write a rule to close the windows when it rains. It is important to recommend rules that are semantic consistency with editing rules. Now, I will detail our approach to solve these problems. Firstly, we build a trigger action knowledge graph. TAC to provide more site information. TAC is a trigger action knowledge graph modeling trigger action rules, devices or services, users, and their relationships. As the figure shows, TAC has an ontology layer and an instance layer. The ontology layer contains a hybrid model with two submodels. Rule collaboration graph. This submodel defines users, rules, devices or services and their collaborative relations. Functionality hierarchy. This submodel defines two functionality hierarchies for triggers and actions. The functions of the triggers and the actions are organized at the high, the medium, and the low levels. Each instance in the instance layer corresponds to a trigger action rule. An instance is also composed of a rule collaboration graph and a functionality hierarchy, which can be mapped into the model on the ontology layer. We perform a schema analysis of top data and construct the ontology layer of the rule collaboration graph. The functionality hierarchies are extracted from UPont, an ontological representation of end-user development in the I. Since conflicts can exist among actions, for example, an action that is to increase the temperature and another to decrease the temperature, we further add the conflicts with relations among functionalities. These relations are used to filter out the rule candidates conflicting with the editing rules. With the functionality hierarchies of TAC, the similarities among rules are calculated in terms of their shared functionalities. That is, the rule similarities can be semantically reasoned by analyzing the categories and supercategories of the triggers and the actions involved in. The conflict relations can be used for semantic reasoning as well. We design Atar to recommend trigger action rules. Atar is a learning to recommend technique. It consists of the following steps. First, context filtering. Atar collects the rule set from TAC, filters out those with devices/services outside current context, and gets candidate rules. Second, feature engineering. For each candidate rule, it extracts 3 types of well-designed features from TAC and trains a ranking model for rule recommendations: the collaborative features, the content matching feature, and the behavior features. Third, learning to rank. A pointwise approach based on a logistic regression model is applied to rank the candidate rules, and returns top in ones. Finally, context conflict detecting. The ranked top in rules will be checked whether they have conflicts with editing rules. Next, I will detail the key steps. Atar is a context-aware recommendation approach. It refines candidate or recommended trigger action rules according to a user's programming context, where the context includes the rules under development and the connected IoT devices or services. Before the learning to recommend stage, Atar performs a context filtering. It guarantees all recommended rules are executed by one of the connected IoT devices or services. When a user is editing rules in I, Atar captures the programming context, including the editing rules in the IoT devices or services. It then retrieves the rules related with the connected devices or services by querying TAC as the candidates. After the learning to recommend stage, Atar also performs a conflict detection. Inconsistent actions and rules are detected and reported during this phase. Note that a rule having conflicts with relations with the existing rules can still be recommended. It relies on the end user to make a decision on either rejecting this rule or accepting it with revisions. To compute the top in recommendations, Atar performs a feature engineering on TAC and trains a ranking model. For each candidate rule and the rules in the current TAP program, we extract several features from TAC for constructing the model. The first type is collaborative-related features. The collaborative features are extracted for both of the user-based and the item-based collaborative filtering recommendations. We extract 5 collaborative features for modeling user preferences. For example, UCF computes the number of paths between the given user and the candidate rule. An intuition is that users are similar to each other if they have written similar rules. ACF computes the shortest path between two rules in terms of their action channels. The shorter the length, the more similar the two rules are. ACCF, TCCF, and TCF can be similarly computed. Although this feature can well recommend TA rules from similar users, or similar TA rules, it is only suitable for TA rules that users have not written, and it is impossible to judge whether users will write the same TA rules. Therefore, it is not enough to use this feature only, and other features are needed to enhance the ability of the recommender system. Content Matching Related Feature, CMF, is designed for content-based recommendation. It measures whether a rule matches the user preference. Since neural network has strong nonlinear mapping ability and can distinguish when user will not like the rule, this paper uses neural network to calculate CMF. Inspired by DKN, firstly TAC is embedded to get the word vector representation of each TA rule. Then, extra information in the knowledge graph is fused to get the enhanced word vector. Finally, the neural network is used to judge the matching degree between the candidate TA rules and the TA rules written by users. Behavior features model the user's repeating behaviors. We extract 3 behavior features from users' history interactions. RPF. It sums up the usage of a popular rule by all of the users. URF. Given a rule R, computes the duplicates of the rule for a user U. Since users may have different repeating habits, it is necessary to model a user and her/his individual behaviors. RRF. It computes the total duplicates of a given rule. Next, I will analyze the evaluation of the work. The evaluation data is extracted from TAP data. TAP programs with only one trigger action rule were deleted because such a project could not be tested. The input of Atar in each training step is all history rules in the TAP program and one candidate rule. And the output is the probability that the user will select this candidate rule to join the current TAP program. Therefore, it is necessary to divide the TA rules and TAP project into written TA rules and candidate TA rules when making data sets. However, only positive samples can be obtained in order to get better training results. Referring to previous work, negative samples were added and samples were made according to the time steps. Recall, NDCG, SR, and SNR are chosen as the evaluation metrics. Recall calculates the percentage of recommended rules and all rules a user really write. NDCG measures whether the rules user want ranked at the top. SR represents the ability of recommending a repeated rule successfully. The higher the SR value, the stronger the recommendation approach in recommending repeated rules. SNR represents whether a user receives at least one repeated rule that the user has never written. The lower the SNR value, the better the approach. We compare Atar with the following state-of-the-art techniques. The evaluation is designed to answer to research questions. The first question is Atar effective in recommending trigger action rules? Comparatively, Atar achieves the highest recall 5 in NDCG 5. Atar leverages the path information and the embeddings of the knowledge graph and designs specific features for learning to recommending trigger action rules. The results imply Atar can effectively recommend the rules a user needs and sort the rules such that highly relevant rules can be placed on highly ranked positions. The second research question is Has Atar solved the cold start problem, the repeat consumption problem, and the conflict problem when recommending the tap rules? Firstly, Atar achieves good results in cold scenarios, indicate that leveraging the knowledge graph helps alleviate the cold start problem. Secondly, Atar takes several factors into consideration, such as a rule's popularity, its repetitiveness, and the user's preference for repeating this rule. It achieves a balance between SR and SNR. Finally, it can prompt users whether their exits conflicts. To sum up, Atar can solve the cold problems, repeat consumption and conflict problems to some extent. Unfortunately, due to the time limit, we do not conduct online tests, which will be done in future work. To conclude, Atar is a semantic and context-aware method for end users to reuse and customize trigger action rules. It constructs a knowledge graph tag for assisting rule recommendations, leverages different types of features for training a learning to recommend model, and actively detects and eliminates potential conflicts among rules. In future work, we will develop a mobile tap programming tool set up with Atar for more data, and end users will be invited to evaluate and to help improve the tool. Thanks for listening.